All right, so it's a pleasure to be here. This is a lot of fun and I think a wonderful idea to bring together the journalists and scientists. So I think as journalists, you often want to know what is the perspective of the person you're talking to. So a little bit of context. So I'm a theoretical astrophysicist. So like Mark, I don't go to telescopes. I've never actually handled data. I didn't have a telescope growing up. So I really come at this from kind of a physics point of view of understanding the physics that goes on in the universe. And what I want to talk about today is how we went from the relatively smooth initial conditions in the early universe to the much more inhomogeneous universe today, like lumpy babies and black holes. And there's a couple of ways one could imagine giving this story. One could focus more on the observational side. I'm not going to do that. I'll talk a little bit about the observations, but I'm going to focus instead more on some of the really large underlying theoretical ideas and key concepts that lie behind our understanding of how structure in the universe came to be. And I really think if you ask from a, say, journalist perspective or from an average citizen perspective, right, why is astronomy important? What is its contribution? I think this is actually the best answer to that, right? Is that astronomy, and this is part of the story that I'll tell you about today, is the modern understanding of creation, the modern understanding of origins, right? Is astronomy and cosmology, how the universe began, how it evolved to form galaxies, planets, stars, and set the conditions for biological evolution. And I'd encourage you, please feel free to interrupt me as I go. I know it's much better to have the questions answered along the way rather than towards the end. So this is a picture of the sky. So this is actually a picture of the entire sky projected in this way. This is taken with the WMAP satellite. This is a picture of the cosmic microwave background radiation. So this is light that fills all of space. What this actually is a picture taken today of what the universe looked like just a few 100,000 years after the Big Bang. And I think, as James Bullock said nicely yesterday, this picture is actually slightly misleading, is that these differences, so what the different colors represent is differences in temperature. And these differences in temperature are actually extraordinarily tiny. The differences in temperature are 0.001% from one part of the sky to another. So filling the universe everywhere is this radiation that basically has exactly the same temperature everywhere on the sky with these tiny, tiny, tiny fluctuations. And this really is, what you're seeing literally is light that was emitted just a few 100,000 years after the Big Bang and then came directly to us. And so that's illustrated schematically. Here, there's lots of versions of this kind of plot. So what this is time. This is us today. This is the very, very early universe. When the universe was very young, matter was so dense that light couldn't travel on straight lines to us. It just bounced around. Kept bouncing around. Eventually, as the universe expanded and cooled, at some point, suddenly the universe became transparent. And the light traveled directly from that time, everywhere, filling the universe, basically on straight lines. And what we're seeing in this image, these tiny little temperature differences on the sky, is the light from when it stopped bouncing around, being scattered all over the place, and started to come to fill the universe on relatively straight lines. So it really is a picture. So here's us. Here's this time, 380,000 years after the Big Bang. We're now 13.7 billion years after the Big Bang. The light from this time then fills the universe. There are these tiny, tiny, tiny fluctuations in density and temperature across different parts of the universe. And that's what this is. This is kind of a record of the tiny differences in density in this early stage in the history of the universe. Yep?
So the colder regions, the blue regions, are the regions of higher density?
Yes, exactly.
That's where the galaxies...
Yes, we'll get to that, exactly. Yep, so the slightly denser regions, slightly cooler, slightly denser regions, are the kind of nuclei, the nucleus, the seeds within which galaxies will eventually form. So this is data, right? This is the way the universe was 380,000 years after the Big Bang, these tiny fluctuations in temperature. This is what we see around us today. The differences in density from one place to another now today, right, are 30, 40 orders of magnitude, not 0.001%, but many, many, many orders of magnitude. Most of space is filled with essentially nothing, very, very tenuous gas, the kind of stuff that Mark talked about, but it's punctuated by things like stars and planets, the Milky Way galaxy, or this is an image of one of the deepest images of galaxies in the distant universe, the Hubble Deep Field. So somehow the universe evolved from these incredibly smooth initial conditions to an incredibly inhomogeneous state it is today, when most of the universe is still filled with relatively tenuous gas, but there are these pockets of very, very dense things like stars and planets and galaxies. The most extreme version of this, the densest objects that we know of in the universe, the lumpiest parts of the universe, are black holes. These are objects that are so dense that they've literally collapsed in on their own weight. Unlike the Earth or the Sun, which are objects where gravity is pulling in, right? Gravity is holding us here on the Earth. Gravity is holding the Sun together. But gravity doesn't win. There's something pushing back out, which keeps the Sun, right, basically the same for billions of years, which keeps the Earth basically the same for billions of years. Black holes are objects where gravity wins. Gravity wins out over all other forces, and the object collapses in on itself to form something in which gravity is so strong that we think that no information can actually get from the inside of that object out. So when we talk about the radius of a black hole, which we call the event horizon, what this really means is that there's some place inside where no information can get out traveling at the speed of light. But if you're outside this radius, this event horizon, then information traveling at the speed of light can get out. So the radius of a black hole is actually a very funny thing. It's not like the Earth, right? The radius of the Earth is the solid surface that distinguishes solid from gas. The radius of a black hole, there's nothing there. There's no matter at the radius of a black hole. It's just a point really that's defined in terms of information travel. Inside of this event horizon, information can't get out traveling at the speed of light. Outside the event horizon, information can get out. Okay? All right. So this really would be a talk unto itself. What are black holes? How do physicists think about them? How did we come to have this idea? Started in the 18th century, but this is kind of a one-slide summary of what black holes are. And really in the context of the story I'm trying to tell you today, they're kind of the extreme version of this contrast between the smooth beginnings and the very inhomogeneous universe we have today, where a small amount of mass has become so dense that gravity really takes over and the object collapses in on itself. Now, if you look at structure in the universe, and James Bullock emphasized this yesterday, it's not that stars and planets and galaxies and black holes are randomly distributed throughout the universe. They're not. They're actually organized in a very interesting way, right? We have stars, which have planets orbiting around stars, usually in roughly the same plane. All the planets orbit around in a particular plane. Stars often orbit around each other, and then stars together orbit around in galaxies. Galaxies aren't just in random places in the universe. Galaxies actually orbit around each other in things that we cleverly call groups. Groups aren't these random things distributed anywhere in the universe. Groups are actually things that orbit around each other in things we call clusters. So there's this kind of hierarchy. There's this organization to structure in the universe, from small scales of stellar systems through to galaxies, through to larger and larger structures. And this is actually a big clue into how structure developed. This is a signature of the role of gravity in forming the structure that we see around us in the universe. So what I want to tell you now is a little bit about how we went from those smooth initial conditions to the more inhomogeneous universe we see. And on the largest scales, the evolution of the universe, how the universe behaves, how it expands and maybe collapses back or expands forever, is really, its evolution is entirely dominated by something that we call dark matter and something that we call dark energy. Dark matter is really just another kind of fundamental particle, something different from electrons and protons, and you'll hear more about this. Dark energy is a little bit more mysterious. It's an energy that is permeating, to the best that we can tell, it's permeating empty space. And I'll come back to the difference between these two in a little bit. The important thing here is that according to our modern understanding of gravity, which is due to Einstein, general relativity, anything that has energy feels the force of gravity. And since most of the energy in the universe is this dark stuff, those really dominate how the universe as a whole expands, how it responds to gravity, because these have most of the energy content. They determine the overall evolution of the universe. And in principle, there's a lot of different fates the universe could have. The universe could have started at some point, expanded out, and it could have been that there was enough matter in the universe that eventually the gravity of the universe caused things to slow down and collapse back in on itself. This is distance between objects as a function of time, expand out, collapse back in on itself. Another possibility is universe expands out and at some point just kind of starts to coast. Gravity stops being very important, things just kind of coast along. What we know from observations now, won the Nobel Prize this past year, is the rather astonishing fact is that we have this intuition from everyday experience that gravity, right, typically causes things to slow down, right? You throw this up in the air, gravity brings it back down. That's the attractive force of gravity. But in fact, the universe is not slowing down, which is what we expected. The expansion of the universe is actually accelerating. And we attribute that to this thing, dark energy. And really, you should just view dark energy as a placeholder. We don't know what it is. It's a placeholder for the empirical statement that the universe is accelerating in its expansion. So this, on the largest scales, this dark energy and dark matter really determine the expansion history of the universe. And what we know now, at least, is that currently the universe is going through a period where it's starting to expand faster and faster and faster. We don't know if that'll continue into the distant future, because we don't really know what this is, so it's hard for us to say what'll happen in the distant future. So this dark energy and dark matter sets the large-scale behavior of the universe within which the structures like galaxies and planets and stars form. And fundamentally, the way that we go from smooth to lumpy is by gravity. Gravity is a relentless, attractive force, except for dark energy. It's a relentless, attractive force that if you start off in the universe with a region that is a little denser than average, gravity pulls things into that region and makes it more massive and denser. And this is an important point. Even though the universe is expanding, so you might think, well, everything's getting further and further apart, so how can gravity bring things together? On top of that expansion of the universe, gravity is nonetheless taking regions that initially or a little colder and a little denser than average, it's taking them and it's making them yet denser and more massive. So these tiny little differences in density, because gravity brings things into regions that are a little bit more massive or a little bit denser, it takes these regions that are a little denser than average initially, and as time goes on, it has billions of years to operate. As time goes on, these regions get denser and denser and denser. And this evolution is really dominated by dark matter, not by dark energy. And the reason is that dark energy is this smooth thing that, as far as we can tell, is uniformly distributed in space. So it's not lumpy. It doesn't have, you don't have regions where there's a little bit more dark energy than other regions, as far as we can tell today. So this growth in structure, gravity bringing things in, is really a process that's dominated by dark matter, not dark energy. And in some ways, this is the fundamental empirical distinction between the stuff we call dark matter and the stuff we call dark energy, is that dark matter is inhomogeneous. It's lumpy. There are regions of the universe that have a lot more dark matter than other regions of the universe. Dark energy is actually relatively smooth. Okay? So that's the picture of how gravity takes these very smooth initial conditions and makes them denser and denser. So this is a numerical simulation of this process. You've seen a number of simulations like this, but it's good to show. Again, because this really gives you a visual image of how the universe went from the smooth initial conditions to the much more inhomogeneous conditions we have today. This is going from early in the universe to later in the universe. Time is marching forward. In astronomy, we often label time by something else that's called redshift. And you can think of redshift as a measure of the typical distance between objects determined by the expansion history of the universe.
I think you should say that you're taking out the expansion. You're not showing.
I was going to say that, right. In this movie, you'll...
Also true in your previous slide.
Yes.
Your description is having taken out the expansion.
Right. Even though universe is expanding.
Right.
Yep. So in this box is kind of expanding along with the universe. So what you're seeing is things collapsing in due to gravity, objects growing from smooth to more and more massive and denser. What you're not seeing is the overall expansion of the universe in the movie. Okay? And the way it's done is the calculation is expanding along with the universe. That's how it's done. Okay? We talked a little bit yesterday about how, and Mark emphasized this today, simulations are only as good as what you put into them. This simulation is just F equals ma. That's the nice thing about dark matter, is that you can explain a lot about the behavior of dark matter just by putting down a bunch of particles and adding up Newton's law of gravity for all of those particles. Okay? So this, in some sense, is a relatively clean calculation, how the dark matter went from smooth to dense, where you now see, go one more time, so we have these smooth conditions where the blue stuff, or the light purple, is less dense. The white stuff is more and more dense. Okay? And what you see is, again, these dense regions get denser and denser. You can see material falling into these dense regions as time goes on. And eventually, these dense regions, gravity gets so strong that these objects are actually held together by their own gravity. And then these objects stop expanding with the rest of the universe. You are not expanding, okay? The Earth is getting further and further apart from other galaxies, but the Earth itself is not participating in the expansion of the universe. And the reason is that it's held together by its own gravity and the strength of the crust. The sun is held together by its own gravity. So objects, when they get enough mass in a small region, they kind of decouple and they separate from the overall expansion of the universe.
The edge of that
Okay.
The galaxy isn't expanding.
Yes.
The local group actually is contracting.
Yeah.
And just ask real fast, so the reason we know that it's dark matter that's responsible for the formation as opposed to normal matter is because there's not enough normal matter?
Correct.
to account for it?
Correct. So the key is that in this pie chart, dark matter outnumbers normal matter by, say, a factor of 10-ish, right? A little less, but roughly. And that, because gravity cares about how much stuff there is, this then dominates that growth of structure. Okay? This is important. It's a non-negligible contributor, but this is critical.
And I'm sorry, the ratio of this pie chart, the ratio of dark energy to dark matter.
Yes.
How do we know that there's so much more?
Right. So this comes from a number of lines of evidence. So one of them is that in these observations of the good. Okay. Thank you. Yeah, I was going to not. No, that's good. That's a very important question that I, in the interest of time, was skipping. Yep.
I have a question to this simulation. It says the simulation of dark matter distribution from the 20 to present.
Yes.
The simulation, you include the dark matter.
Yes.
Does it matter where you put it? Is it spread out equally, or do you put it in different?
You put it initially with small differences from one place to another, which are distributed in a way that is consistent with the kinds of fluctuations that we see in the microwave background. Extrapolated, so this is very early in the history of the universe. The simulations don't start here, they start further forward in time. So you kind of take this, extrapolate it forward to some point, and then start the beginning.
So randomly, this is like
It's, we know statistically, we know on average how the density differs from one place to another. And you start out with differences in density described in this particular statistical way.
So Mike Norman in the first talk yesterday explained that there's this one theory, the cold dark matter theory,
Yes.
cosmological constant, that both correctly describes in every detail the statistics of the cosmic microwave background and also provides the starting point that gives rise to all the kinds of structures we see on all different big scales.
Okay. So
It's a cold dark matter model that's the basis for all of that.
So this is another numerical simulation of the formation of structure, dark matter only. This is actually the difference is that in this simulation, there are many, 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 many galaxies. This is a very large region, hundreds of millions of light years across. This next movie is of a simulation that's only 1 million light years or so across. This is a simulation of the formation of a galaxy like the Milky Way, the dark matter of a galaxy like the Milky Way. This is like the simulation that James Bullock showed. And one of the things you'll notice is that the objects start off small. So you'll initially see very small dark matter lumps when the redshift is high, when the universe was younger, smaller. And then as time goes forward, things get larger and larger and larger. This is a property of the cold dark matter model, that the structure in the universe starts out small, and then as time goes forward, it gets larger and larger and larger, more massive. You start off with small bound dark matter clumps, and then those bound dark matter clumps get larger and larger and larger as time goes on. So the reason for emphasizing the dark matter is that really this distribution of dark matter, again shown here, where you have this very filamentary structure where the white regions are dense regions with lots of dark matter. The purpley regions are low density regions with not much dark matter. This filamentary structure of dark matter really is the backbone that on the largest scales, this distribution of dark matter determines where the stars, galaxies, planets, black holes, and people are going to end up. Galaxies form in regions where there's a lot of dark matter because the dark matter, right, in this region where there's a lot of dark matter, it pulls in the normal matter. The gas flows in via gravity towards the dark matter. Yep.
Even those very small regions
So the differences in density are very small initially. This is an image of the present-day distribution of dark matter. In this image, the differences in density are many orders of magnitude. So they started off, everything started off the density the same to 0.001%. As you march forward, gravity makes the dense regions get much denser than average. So now there are regions where the dark matter density is enormous compared to the average of the universe. Is that what you were getting at?
Well, sort of. I guess I'm just wondering at what point, how much density needs to be coupled.
So there is a magic number. It's 200 times the kind of average density of the universe. And that is the kind of reason for that is not obvious. But when a region becomes sufficiently dense, then it decouples. Its own gravity wins out over the expansion history of the universe. And the magic number is about 200 times the average density of the universe. Continue to, that's right. Yep. Okay. So in a very real sense, when you look at distribution of galaxies, and this is the Sloan Digital Sky Survey distribution of galaxies on the sky, we're sitting here. This is going further away from us on scales of 1 billion light years or so. The distribution of galaxies in data like this really is, in a real sense, tracking the distribution of dark matter. Not perfectly, but pretty well to first approximation. Okay. So where does gas and stars and normal matter, the stuff that forms stars and galaxies and planets and ultimately people, where does that come in? Well, the first bound dark matter clumps formed a few 100 million years after the Big Bang in this redshift number. That's a redshift of maybe 20 or so. And the first galaxies, this is a series of snapshots of a numerical simulation of one of the first galaxies. It's actually done by Mike and his colleagues. The first galaxies were very small. Remember again, structure started out small and became bigger and bigger and bigger as time went on. The first galaxies maybe had a mass of 10,000 or 100,000 times the mass of our sun in dark matter. For comparison, our galaxy has a mass in dark matter that's about 1 trillion times the mass of our sun. The first galaxy had a few handful of stars. Exactly how many, we're not sure. That's an area of research compared to our galaxy today, which has trillions of stars or so. And Steve Ferlinetto in the afternoon is going to tell you more about this process of the formation of the first stars and galaxies.
I want to return just for 1 second about that figure of the 200 times.
Yes.
That's within the region of difference that Mark was talking about this difference between the density of atomic hydrogen and the density of molecular hydrogen.
Correct. So the average density in the average, so the statement I made, to be more precise, is that when a region is roughly 200 times denser on average than kind of the background universe, it starts to decouple from its surroundings. Within that region, once it's decoupled, gravity still makes things denser and denser and denser, forming the atomic and molecular gas that Mark talked about. So 200 times the average density is still much less than the densities that Mark was talking about. But that 200 times number is roughly the distinction between things that start to collapse in on themselves and have the chance of forming stars and molecules and things like that, and things that don't. Okay, so you'll hear more about this for stars and galaxies later in the afternoon. So I'm going to focus really on the formation and growth of galaxies and black holes. And so the point I want to emphasize now is that more or less instantaneously from the point of view of the universe, as soon as you have the first stars, you have the first black holes. And the reason is that the stars that form black holes are these very massive stars, we think. And very massive stars don't live long by astronomy standards. Very massive stars only live for a few million years before they collapse in on themselves to form black holes. So, right, in stars, stars are this kind of balance between gravity pulling in and the hot pressure of the interior pushing out. And what keeps stars hot is nuclear fusion. And so as time goes on, you fuse hydrogen to helium to carbon all the way up to iron in your blood, right? That's fusion in stars. And that keeps the star hot, which balances gravity. But eventually you run out of hydrogen, helium, carbon, et cetera. And for massive stars, stars that weigh maybe more than 30 or 40 times the mass of the sun, after this happens, they collapse in on themselves to form black holes. And that takes just a few million years. And for comparison, right, the first stars form a few 100 million years after a black hole. After the Big Bang. And so that means it takes a few 100 million years for the first stars to form, and then 1 million years later, which is like that, right, from the universe's point of view, 1 million years later, the first black holes form. And the first black holes weigh maybe 10 times the mass of our sun or so. So in the history of the universe, we've gone from the smooth initial conditions of the Big Bang through to the formation of the first stars, the first galaxies, and the first black holes. And we're not at 13.7 billion years. We're really at just maybe a few million years after the Big Bang. A few 100 million years. Thank you. OK. So as we go from here, a few 100 million years after the Big Bang, to the present day, we've seen how these bound dark matter structures, things that are held together by their own gravity, which are not expanding with the expansion history of the universe, those get bigger and bigger and bigger. Dark matter lumps start out small and get bigger and bigger and bigger as time goes on. And because there's more dark matter than normal matter, it's really those bound dark matter clumps that set the conditions for where galaxies and stars and planets are going to form. So within those dark matter regions, how do stars and gas behave? How does the stuff that we actually see and the stuff that we're made of, how does it actually behave? There's basically two, to simplify it, there's two ways we think that the stuff we can actually see, gas and stars, grows as we march forward in time from here to here. One is that gas continually streams into these dark matter, bound dark matter regions that we call halos. Okay? And this streaming is along this filamentary structure that you saw in the previous pictures. So this is a numerical simulation. The red is dense gas streaming into one of these dark matter regions. And this dense gas is really the fuel that will then power the formation of stars and the formation of galaxies.
So it doesn't get dense enough in those streams to form stars within the streams, is that right?
Correct. That's what we think. That's right. The other way that you can form bigger and bigger objects is things start out small, but then as you saw in those movies, they're kind of constantly bombarding each other. So the other way that galaxies get bigger is they collide with other galaxies. And that merging process builds bigger and bigger galaxies. And these are actually images taken with the Hubble Space Telescope of colliding galaxies. They look like train wrecks, because that's what happens when galaxies collide, is all kinds of interesting things happen. Stars get flung off into the outer parts of the galaxy. And so, to simplify it, these are the two basic ways that you continue to grow galaxies as time goes on. So I've presented a very simple picture, which actually, to zeroth order, you can understand a lot about the properties of galaxies with this very simple picture of galaxies and stars follow the dark matter. this is the dark matter in the present universe. You can take these regions with lots of dark matter and just say there's going to be a big galaxy where there's a lot of dark matter. And to first approximation, that actually does a decent job of explaining where the stars are and where the galaxies are. But in detail, it doesn't work well. Okay? And that's why galaxy formation is not a solved problem, because it's not as simple as the gas just following the dark matter. And the reason is that once the gas gets into galaxies, it really stops following the dark matter. Once the gas gets into galaxies, all the stuff that Mark started to talk about becomes important. I have to worry about, is it atomic gas? Is it molecular gas? I have to worry about the fact that stars, when they die, blow up and put huge amounts of energy into their surroundings. I have to worry about the fact that the radiation from stars heats up surrounding gas and pushes it around. Okay? And so one way to phrase the problem of why galaxy formation is actually a harder problem than gas following dark matter is that, in fact, most of the gas that at some point in the universe's history made its way into a galaxy made its way back out again. Okay? It didn't just sit there and turn into stars. It gets blown back out by these complicated stellar processes. The fact that explosions of stars and stellar winds and radiation from stars churn up their surroundings. And these are images. This is an X-ray image, and this is an image of the Hubble Space Telescope showing you this is the galaxy here. And this is hot X-ray emitting gas getting blown out of the galaxy. The gas is heated up by stellar explosions. Here, this is the disk of the galaxy. And you again see gas being blown out of the galaxy by these stellar processes. And this is what we kind of generically call feedback. It's the fact that the formation of structure is not a one-way street. The gas doesn't just follow the dark matter. Once the stars start to form, the process gets a lot richer and a lot more complicated. And it's not just simple gas following dark matter. We have to worry about a lot more physics. And that's the fundamental challenge of galaxy formation, is understanding all of this physics and how it affects the subsequent history of the kind of gas in the universe. So this is a simulation we've done just to give you a visual image of how much more complicated the process actually is. So this is an image of a region that's about the size of the Milky Way galaxy, or will become a galaxy like the Milky Way in the present day. And in this simulation, you're actually observing gas now. And we've tried to include these processes like stellar explosions and radiation from stars heating up surrounding gas. And what you see in the distribution of gas here, this is the temperature of the gas, is it literally is like a bunch of bombs going off in the universe. You have stars forming, which then dump huge amounts of energy into their surroundings, which blow gas out of galaxies, which completely change how the gas in the neighborhood of that galaxy behaves. And this is just a kind of visualization of this argument that it's not a one-way street. And so this really is the kind of frontier of our understanding of galaxy formation now, is trying to observationally understand the role of these kinds of stellar processes and to theoretically include them in our numerical simulations. These are much more, well, okay, I was going to say these are much more than F equals ma. Not really, because everything is F equals ma if you use the right F and the right A. But there's a lot of physics involved in modeling these kind of stellar explosions and things like that that's complicated. And so we try to do a good job, but it's hard. Okay. What about black holes at the centers of galaxies? So we think now that every galaxy has at its center a massive black hole. Where did those come from? Well, they probably came from the first stars. The first stars we think were relatively massive. They collapsed to form black holes that only weighed about 10 times the mass of our sun. And then as the universe evolved from a few 100 million years after the Big Bang through to billions of years after the Big Bang, black holes grew from 10 times the mass of our sun to up to 10 billion times the mass of our sun.
If we're not sure how massive the first stars are, why would the first black holes be roughly 10 solar masses?
So roughly means they could have been 3 and they could have been 30, and it doesn't matter for what I'm going to tell you. So it's as long as there were some massive stars, then there would be some black holes formed in the relatively early universe.
And so those rough masses are based on roughly what we think?
Yes, and Steve's going to talk more about this, exactly. Yep, okay. So just to give you a sense of spatial scale, if you took our sun and shrunk it down so its radius was a few miles, it would be a black hole. If you took an object that weighed 1 billion times the mass of our sun, the size of its event horizon, the point of no return, would be about the size of our solar system. Okay? For comparison, the size of our galaxy is 1 million to 10 million times the size of our solar system. So black holes at the centers of galaxies are really, really tiny objects. And so actually it's a very interesting and difficult and not solved problem of how do you grow those black holes at the centers of galaxies. How is it that they grow, this tiny region at the center of a galaxy, how does it grow from weighing 10 solar masses to weighing 1 billion solar masses? So I want to emphasize this because this is more or less the opposite of the popular conception of black holes in both reasonably literate scientific popular press and books, and certainly in popular culture. The prevailing view of black holes is that they suck in everything, and this is fundamentally wrong. Okay? Black holes are not in any way a cosmic vacuum cleaner, which easily sucks in everything in their surroundings. And one way to state this is that the Earth doesn't get sucked into the sun. We happily go around and around and around. And if you were to get rid of the sun and replace it by a black hole that weighed the same as the sun, the Earth would not get sucked into the black hole. It would happily go around and around and around. Okay. So the problem of growing black holes at the centers of galaxies is actually a very serious and important scientific problem. And it's fundamentally a problem in this fact that matter, when it goes around and around and around, it's happy to do that. For the physicist, right, it has angular momentum. It likes to go around. It doesn't want to get rid of that angular momentum and fall into the center. Okay? And really, it's only when you get very near the event horizon of a black hole that gravity starts to behave in a very strange and counterintuitive way. Far away, Newton got it right. And so we would no more get sucked into a black hole if there were a black hole at the center of our solar system than we will get sucked into the sun. Yep?
This might be a really dumb question, but how is an active galactic nuclei different from this?
2 slides. Yep, good question. So just to wrap up then, how do we think you actually get gas to the centers of galaxies to grow black holes? Well, this is a very active area of research. These are 2 numerical simulations illustrating some of the processes that we think are important. This shows the collision of 2 galaxies, and the red and the green stuff is gas. Not stars, not dark matter, but gas. And what you see is that during the collision of the galaxies, the gas goes from being distributed on a large scale. Some of the gas gets funneled into the center of the galaxy. And the reason is that matter likes to go around and around and around only if gravity is relatively simple. If matter is distributed spherically in an average way, if it's the same in every direction, then matter happily goes around and around and around. When gravity is very asymmetric, like in the collisions of galaxies, you can torque matter and drive it to the center of a galaxy. That's what's shown in this movie. This is a zoom in of the very center of one of these galaxies following the gas. And what happens is these asymmetries in gravity efficiently create these very asymmetric structures in the gas, which funnel gas to the center of the galaxy and allow the black hole at the center of the galaxy to grow. So this is my view. Here's where my own research comes into the story. This is my own particular view of how we actually get gas to the centers of galaxies to grow black holes. There are other ways that you can grow black holes. Black holes can grow by swallowing stars. They can grow by colliding with other black holes. As galaxies merge, black holes merge. These happen, but they're subdominant to gas getting to the center. So the last point I want to make is that in the last 10 years or so, there's been a very important observational clue about the connection between how black holes at the centers of galaxies form and grow and how galaxies themselves form and grow. And that observational clue has at its heart to do with the fact that there are really two different types of galaxies in the universe we see around us. There are disk-like galaxies or pancake-like galaxies, and there are spherical galaxies. This is actually more general. Basically, everything in the universe is either a sphere or a disk. And there's a good reason for that. Either things are rotating a lot, in which case they form disks or pancakes, or they're not rotating a lot, in which case they're pretty spherical. Okay? So there are these two types of galaxies. They're not mutually exclusive, right? You see at the center here, there's a little bit of a spherical component to the galaxy. But to first approximation, galaxies have a disk-like component and a spherical component. And what we've learned over the last 10 years or so is that the presence of massive black holes in galaxies depends critically on how much of this spherical part of a galaxy there is. How much mass is there in the spherical stellar distribution in a galaxy? And it doesn't care as much about how much of a disk there is. So the presence of the black hole depends a lot on the spherical part of the stellar distribution and less on the disky part of the stellar distribution. And this is kind of a schematic illustration of that basic observational fact. If you make a plot of the mass of a black hole as a function of the mass of the spherical part of the stellar distribution, what we call the bulge or the elliptical stars in a galaxy, bigger black holes live in bigger galaxies. But not just bigger galaxies, they live really only in bigger bulges, bigger galaxies with more of this spherical stellar distribution. This probably sounds kind of tautological, right? Okay, bigger galaxy, bigger black hole, no surprise. Nonetheless, this has generated a tremendous amount of interest and excitement and enthusiasm. And it's not because, this trend is maybe qualitatively makes sense. Bigger galaxy, more stuff, bigger black hole. The surprising thing is just how regular this trend is. The black hole at the center of a galaxy, on average weighs about 500 times less than the mass of the spherical stellar component in a galaxy. This is true over a factor of 1,000 in galaxy and black hole mass. And that kind of quantitative result is what has generated so much excitement. Now, why should the presence of black holes care about the spherical distribution of stars and not about the disky distribution of stars? And the physical reason for that, the basic physical picture, is that how do you form a spherical distribution of stars rather than this rotating distribution of stars? Well, what you have to do is you somehow have to get rid of all of this rotational motion. Well, how do you get gas to the center of a galaxy to form a black hole? You somehow get rid of all of that rotational motion. So forming the spherical distribution of stars really requires the same kind of physical processes as getting gas to the center of the galaxy. It requires getting rid of all of that angular momentum, or that sense of rotation of gas and stars and galaxies. And that's the fundamental reason that we think there's a link between kind of the stellar mass of the spherical part and not the disk-like part of galaxies. Why are black holes 1/500th of the mass of their spherical stellar distribution around them? This is actually a kind of remarkable result. So an analogy is, imagine you go into every room in this building, and at the very center of every room is a little ball of dust. And the ball of dust at the center of the room is exactly 1/500th in size as the room as a whole. Why should that little tiny thing at the center of the room, why should the little tiny thing, the black hole at the center of the galaxy, whose gravity has no effect on the galaxy as a whole, no effect, why should the black hole's mass know about the mass of the galaxy hundreds of thousands of light years away? What is the possible causal connection between what happens at the very, very center of the galaxy and the larger scale galaxy as a whole? And what we think is that that causal connection is provided by these active galactic nuclei that were alluded to. It's one of the wonderful paradoxes that black holes, right, objects which are defined by the fact that no light can escape their gravitational clutches, nonetheless, black holes produce the brightest sources of radiation, the brightest sources of light that we know of in the universe. So how does that happen? It's not the black hole itself. What it is this process of gas spiraling in towards a black hole, gas getting funneled in towards the black hole at the center of the galaxy. As the gas gets funneled in towards the black hole, it starts to move at nearly the speed of light. And in that process, the gas gets heated up to enormous temperatures. And as it gets heated up to those enormous temperatures, the gas radiates huge amounts of energy. And that process then of funneling gas to the center of a galaxy is the process that produces gas getting funneled onto a black hole at the center of a galaxy, produces the brightest sources of radiation that we know of in the universe. These are called active galactic nuclei, quasars, radio galaxies, lots of different names. There are a variety of observational manifestations of gas getting funneled into black holes at the centers of galaxies. This tiny region at the center of a galaxy, no bigger than our solar system, shown in this image here taken with the Hubble Space Telescope. This region, no bigger than our solar system, can produce more light than an entire trillion stars in a galaxy, hundreds of thousands of light years across. Okay? And that's because gas spiraling into a black hole at the center of a galaxy is the most efficient way of turning mass into energy, light, that we know of in the universe. Much more efficient than nuclear fusion in stars. And this is really the causal way that black holes affect their surroundings. The way we think that what sets the mass of the black hole at the center of a galaxy has nothing to do with its gravity. It's that this puny region at the center of a galaxy is actually a huge source of energy. And as the gas spirals into the black hole, produces light that streams away from the vicinity of the black hole, produces outflows that stream away from the vicinity of the black hole, that radiation and light can actually have a huge effect on how gas in the galaxy behaves. So just like we talked about how stellar explosions affect the subsequent formation of stars, gas spiraling into a black hole at the center of a galaxy, producing huge sources of radiation and outflows, that actually has a huge effect on the behavior of the gas in galaxies. And I've illustrated that with a numerical simulation here. This is a region near the center of a galaxy. There's a black hole. Gas is spiraling in towards the black hole. But as it does that, some of the gas doesn't spiral into the black hole, but gets blown away again in these outflows, just like Mark talked about for forming stars. As stuff spirals in, not all of it goes in, some of it goes back out again. And that literally is like putting off a little bomb at the center of the galaxy. And it blows material away. And so we think fundamentally what regulates why black holes weigh 500 times less than the galaxies in which they sit is that the black holes probably got as big as they could before their outflows and radiation were so strong that they had a tremendous effect on gas everywhere in the host galaxy. A big enough effect that it really regulated how the black hole grows and how perhaps even stars in the galaxy grow. And so that process, this process of gas spiraling into black holes at the centers of galaxies, producing light and outflows, that is the fundamental causal connection that regulates how black holes at the centers of galaxies grow and have the properties they do. Okay, so I'll end there, and I hope I've given you a feel for how we went from those smooth initial conditions set down during the Big Bang to the inhomogeneous universe, including the most inhomogeneous objects we know, black holes at the centers of galaxies. So thanks.
There's been some suggestion that the feedback mechanism is not required for the galaxy black hole correlation, and instead that mergers might build up this correlation, just possible mergers over time.
Yes.
Could you speak to how that idea is standing in the community as opposed to this feedback mechanism?
It has been suggested. So mergers certainly do play a role in shaping the properties of galaxies and probably the properties of black holes at the centers of galaxies. And for the most massive galaxies, which weigh trillions of solar masses and stars alone, and for the most massive black holes, which weigh billions of solar masses, mergers might indeed shape their properties, but not for typical, I think for typical black holes and typical galaxies, that's a subdominant process in setting their properties. I think that's my own view, and I think that's probably fair to say that that's the consensus view, although this is very much an active area of research.
So this idea that active black nuclei can spew away Alpha radiation and change the gas dynamics in a galaxy. So could you argue that those are younger black holes, that they haven't spewed away everything yet, and that they're still like pulling things in and spitting it back out? At some point in time, it'll be gone.
Right, so we do see that happening around us in the universe today. In fact, one of the puzzles that confused people for a while, though I think now it's understood, is that, so I told you here that dark matter structure starts off very small. The lumps of dark matter held together by their own gravity start off small, and they get bigger and bigger and bigger as time goes on. If you look at galaxies, that's kind of true in an average sense, but there is an interesting puzzle, which is the most massive galaxies today aren't growing at all. They formed all their stars when the universe was younger. The most massive black holes in the universe today aren't growing at all. They gained all of their mass when the universe was younger. The galaxies and black holes that are actually growing today are not the most massive ones, which you might naively think would be true from this picture, but it's actually ones that are a little bit less massive that are still growing today. So we see this process happening around us. Black holes still growing, galaxies still growing. It's not the most massive galaxies and black holes that are growing today. It's ones that are a little bit less massive than average. And as we look back when the universe was a little bit younger at a few billion years ago, then we see a typical black hole at the center of a galaxy. And a typical black hole at the center of a galaxy weighs about 100 million times the mass of our sun. And it gained most of its mass 3-4 billion years ago. It's not growing much today. It grew when the universe was a little bit younger. But we certainly do see examples of that process continuing to happen today.
Let's thank Eliot.